Welcome learner for the lecture 13 of a differential geometry. Let us go next topic that will be considering as a matrix on the surface, the first fundamental form. Okay. Analogous to the actual length ds square in the case of a space curve, we shall introduce the matrix on the surface called as a first fundamental form. Let R equals to R UV be the given surface. You know that UV consider as a domain of the form. Let the parameters UV be the function of a single parameter t, and R equals to V of a UTVT be the function of a single variable t, and hence it is represented on the curved surface with respect to t as a parameter. The arc length in the term of the parameter t is given by ds upon dt square equals to dr upon dt into dr upon dt square for the multiplication. This is the first equation, and you know that dr upon dt for the partial derivative del r upon del u into del u upon del t plus del r upon del v into del v upon del t. Okay, this is the first and second equation. Using equation 2 and 1, we get ds upon dt square equals to r1 du upon dt plus r2 dv upon dt whole square. Okay, then fraction to the form r1 into r1 du upon dt whole square plus 2 r1 into r2 du upon dt into dv upon dt plus r2 into r2 du upon dt considering as a square. Okay, let E equals to R1 into R2 means R1 square, F equals to R1 into R2 they generated, and G equals to R1 into R2 R2 square. Okay, put to the equation in the term of a differential form, that is a ds square equals to E du square plus 2F du dv plus G dv square. Then definition 1 considering to the form, this is 5 equation. Differential quadratic form 5 is called as the first fundamental form of the matrix on the surface. It is usually denoted by the I. Let P and Q be the two considering as a point on the surface with the position vector R and R plus dr corresponding to the parameter UV, and U plus du plus V plus dv generated. Now dr equals to dr upon del r upon del u du plus del r upon del v dv equals to r1 du plus r2 considering as a dv is the first equation. Then first definition will be considering P and Q the 2 points with considering as a length ds with the elements of the joining to the equal point, that is a mod of a dr. Then equation 1 will be given as ds square equals to dr into dr equals to dr square means r1 du plus r2 dv square, r1 square du square plus 2 r1 r2 du dv r2 square dv square. Okay, you know that this is a form E du square plus 2f du dv plus G dv square. Thus, if ds denote the length of a elementary arc joining to u and v, u plus du, v plus dv lying on the both surface, that is a ds square equals to E du plus 2f du dv plus G dv square. This is equation 2. From equation 2, we get to the form, that is a ds upon dt whole square. Differentiate equation 2, then get it as a form E ds upon dt whole square plus 2f du dt dv dt plus G dv upon dt whole square. Hence equation giving s equals to integration 10 to t square root of a E du upon dt whole square plus 2f du upon dt into dv upon dt plus G dv upon dt whole square dt. Okay, let us go theorem first. The first fundamental form of a surface is a positive definite quadratic form du and dv. Proof will be considering to the form. The quadratic form q equals to a11 x1 square plus 2a12 x1 x2 plus a22 x2 whole square for the real value of a x1 and x2 is called as a positive infinite definite form, that is a q always greater than 0 for every point x1 x2 is not equals to 0 form. The condition for the q is a positive definite r to the form a12 equals to a21 a11 always greater than 0, a11 a22 minus a12 whole square is always greater than 0. Then equation 1 verified that I equals to E du square plus 2f du dv plus g considering to the form that is a g dv square. This is equation 2. You know that satisfy the positive definite quadratic form. Then consider only to the ordinary point r1 into r2 is not equals to 0 and h square equals to r1 cross r2 whole square is greater than 0. Now h square equals to r1 into r2 whole square equals to r1 into r2 dot r1 into r2. Considering both of the same condition, then multiply to the form r1 square into r2 square minus r1 into r2 whole square equals to eg minus f square. Since condition is given that h square is greater than 0, always eg minus f square is greater than 0. And also we have to the from the definition of E, r1 into r2 equals to r1 square greater than 0, g equals to r1 into r2 is greater than 0. Hence equation 2 satisfy the condition 1 for the positive definite quadratic form. So we get it E du square plus 2f du into dv plus g dv square. Then put up to the value half is common to the form E du plus f dv whole square plus eg minus f square dv square considering. Since eg minus f square is greater than 0, e is greater than 0, I is always greater than or equals to 0. So to prove that I is a positive, we have to show that I is not equals to 0, then positive condition will be given in all satisfying form, that is if possible let I equals to 0, then implies to the equation 1 E du plus f dv square equals to 0 and eg minus f square dv square equals to 0. Okay, second condition will be given to the form eg minus f square is greater than 0. We get to the from dv equals to 0. The above condition 2 reduces to the form e du plus f dv equals to 0 and dv equals to 0, which implies e du equals to 0 since E is not equals to 0, D equals to 0. Thus, we have to the condition to satisfy the all constant are not constant because getting to the value. Thus, we get I is not equals to 0, so that I is always greater than 0 for the first fundamental form of the equation.